Thank you. Thank you for attending this panel. I believe that there's going to be some very interesting things said by this panel that, one, you might have heard them before, but I'm sure that they will come and look at the problem in a very different angle. And so it'll give you a chance to perhaps think about what you've heard from a different perspective. And I know that I've always gained a lot when I've had that chance. I'm John Thomas. I'm the panel moderator. And let me introduce our panel to you. First, we have Eric Gebhardt. Eric? Eric is GE's CTO, Chief Technology Officer, and Vice President of Engineering at GE Gas and Oil. Next, I'd like to introduce David Long. David is the president of INCOSE. INCOSE stands for the International Council on Systems Engineering. He's also the founder of a software environment company called Vitech, V-I-T-E-C-H. We have Paul Nielsen. Paul is director and CEO of the Carnegie Mellon Software Engineering Institute. We have Greg Panon. Greg is the president of Control Tech Analytics. We have Don Burns, who is the head of innovation in systems engineering at Rolls-Royce, and John Wade, who is professor of systems and professor at the School of Systems and Enterprises at Stevens Institute, and the chief technology officer for the Systems Engineering Research Center that is also housed there at Stevens. Let me explain how we're going to have this panel unfold. I don't know about you, but if I was in the audience, I'd be a little frightened of a panel whose schedule is for 3 hours.
Yikes.
Right?
Yeah.
Right. I've been in these panels that have been scheduled for 2 hours, and I know the pain. So we're going to do this a little bit different. The first thing that we're doing is we're going to break this up so that there will be 3 speakers of my august colleagues talking first about their perspectives on integration and complexity of systems. And then we're going to sit down, we're going to have a dialogue. I'll probably have a couple of questions. I would ask you to pose some questions. After that session comes to a natural end, wherever that energy is, and you know and I know that that energy, could wave over time, we're going to take a short break. Now, I would ask you, unless we have been absolutely boring you to tears, to please come back. Because I have 3 other colleagues who are going to share with you their perspectives. And this august group is very senior and comes from a very different set of perspectives. It's a perfect mentoring time of, quite frankly, sages. I know I'm looking forward to be able to hear their perspectives. We're going to do it again. 3 people are going to give you perspectives, and then we're going to have another dialogue. And when that ends, we're done, whatever that timeline is. I have done this before where we had to call time after a couple hours because people actually were very interested, and there were lines on the mic. That's my personal goal, but we'll see how you feel. Okay? Now, the next objective that I want to propose to you is this is a nice size, intimate group. Please be comfortable on raising your hand, asking questions, engaging with us, okay? Because that's what we would like to do, is engage with you. Now, I mentioned that I'm the moderator, but a little bit of my background is that I'm a retired Air Force. I'm a retired senior leader at Booz Allen Hamilton, as well as its chief systems engineer. And I had the honor of passing to Dave Long in January the baton of being president. So I'm a past president of the International Council on Systems Engineering. With that, I'd like to be able to give you a little bit of a presentation. The purpose of this presentation is to try and set in a context two concepts, truly. This thing called systems, you know, sometimes drives people batty, right? It's recursive, and there's an abstraction. I want to give you a simple notion of how to think about a system. The second thing I want to share with you is a notion that hopefully you can take away about integration, okay? And I already lied to you. The third thing I'm going to try to do is put into context this other very broad idea of complexity, okay? Now, here is the most simple definition that I think has proven to me to be very useful of a system. A system is something that is made of parts, and the parts are not in a bag by themselves. They're interacting together, and they interact to produce a behavior. That's a system. Now, you could go as small as a can opener. You could go as big as NASA's system that effectively put men on the moon. That definition will apply across that whole range. Let me give you an example, though, that I use most of the time. A car. A car can be thought of as three parts. A car is built from a body and a chassis and an engine. Okay? So there's the thing. The body, the chassis, and the engine have to interact together to generate the behavior. In this case, a behavior of a high-speed curve with other quality of service constraints. That's the behavior. Now, here's the test. You see, the chassis can't do that behavior, right? And the engine and the powertrain can't do that behavior, nor can the body. It's only through the proper interaction of the body with the chassis and the powertrain that you can deliver that. So that's the thought of a system. That's the fundamental thought of a system. Many times when you hear about these huge program overruns, and I don't care which domain you are in or industry, what you'll normally find is people have built a lot of parts. And the real problem is they're only a bag of parts because they're not interacting in the way the investment is. So I hope that that's a useful takeaway for you. The second thing I want to introduce is the concept of integration. Okay? And to make it worse, it's actually multidiscipline. But think of integration as worrying about the issues of the parts connecting together and interacting the way they're supposed to so that you just don't have a bag of parts. Now, you can think of integration from a technical point of view, the physical parts, right? But there's actually process. There is actually teams and organizational integration issues. There's human interconnectivity. There's even policy. Any policy wonks here? Wonderful. A systems engineer and a systems integrator is your best friend because you think of the system in the most macro scale. And we know how to help you specify the policy objective in a way that makes it measurable. We can be your best friends. Now, the issue that you'll see, depending on your audience, is you can have an audience who's completely oriented in the physical domain, and they'll only worry about technical integration issues. There's nothing wrong with that, except that very, 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 very few things ever spell success by finally having it put together and not having it immersed in society, within its rules, within its business processes, within its teams. And so this becomes quite complicated. Let me give you an idea then. I talked about the car. So it can be a technical integration problem of those three things. From a technical perspective, it's the engineered interfaces that are either going to make or break this thing from becoming just a bag of parts, very expensive parts, or something that meets a behavior objective of an investor. Another example is this: I'm going to take this idea of the car, but I'm going to up the system definition to a racing competition. Now, when we think of that, we know and have seen that there's a lot of very, very expensive cars. Okay? All of them are built from 3 major parts: a body, chassis, and engine, and they pay millions of dollars for these cars to have a certain level of system behavior, which is very high performance. The system behavior, like we had mentioned with the policy support, is a much higher abstraction. It isn't, I want a car to take a 60-degree turn at 160 miles an hour. The abstraction is, my objective for the behavior is to be the first to cross the finish line. Now that's interesting. Delivering the car is an important part, but there's organization and there's process that if those fail, if you've ever watched a racing competition, they'll never get across the line. So those parts have to not only integrate with each other, but they have to integrate with the physical entity of that car. There is policy stuff. Those cars are tremendous safety hazards, both on the ramp as well as to the observers. And those policy issues have to be integrated in. Otherwise, you could build a car that actually works wonderful, but would not be able to be certified to race on a given race. And time again, humans become part of a larger system that have to have integration addressed. So that's a way now to bring this idea of the car, of the physical system built from some parts that have to interact together to deliver a behavior, up to a much higher level of abstraction. Now with integration, the focus is on interfaces. The bottom line is interfaces and connections. Interfaces are like the nodes, and the connections are the interfaces. Follow an n-squared type of phenomena. Now what I mean here is if you've got 2 nodes, you got 1 connection, right? But if you have something like this 5 or 6 or 7 or 8 nodes, the connections start getting complicated. You can just think that if somebody is worrying about every connection, you can see how many more people on your team you have to have. So that's one aspect of integration, but it isn't the scariest one. The scariest one is that the number of interfaces drive the number of states of a system. And that can generate behavior that is very destructive and unexpected, depending on whether you've controlled that properly. In this case, the states go as n factorial, not an n squared problem. What that really means is for that 15 connection n number 6 that I had mentioned before, you're up to the 30th power of states. That's astronomical. And that's why so many unexpected things happen. And because everything is now working and you're attempting to get these hordes of team members working together to connect everything, there's marching armies who are spending money on an hourly basis, trying to be able to keep control of this. So there now is why integration is such a critical issue here and in the science. So systems engineering and integration is focused on minimizing that hairball of that difficulty. And let me emphasize this notion, you know, those nodes and that e to the 30th power, that's a real software diagram in which the x-axis portrays about 15 nodes that are CPU interfaces on a car and the interrelationships. Now, they fixed that problem, but that's the notion of just how wildly and quickly these states can get away with it from you. So I'm going to transition to introducing our first speakers, but I forgot I wanted to ask a demographic couple of questions. Just quickly, how many people are in the aerospace business? Okay, so a lot of us. Students or in universities? Okay, great. Any electric utility power people here? Well, bravo. My hat's to you, sir, and thank you for coming. Here's a very different angle. How many people are wearing watches? There we go. How many people just simply use their smartphone? Yeah. Isn't it interesting? My daughter told me a while back, this is, as a matter of fact, this is what caused me to finally put my watch away. I said, why in the world don't you wear a watch? And she goes, a watch? That's a single function device. Why in the world would I want to go ahead and spend time with a single function device? I was going, that's kind of frightening. Lastly, I think I'll transition with a quote that John Glenn made. As he was hurtling through space, he said, you know, I realized while I was up in space, going around the Earth the first time, that every part of this rocket went to the lowest bidder. Now, what's neat in that conversation, for me, is the fact that, but every part did its job, and its job was pre-specified by a systems engineer. And people who took ownership of the leadership responsibilities of having the parts work together is what made that happen. I'm proud to be a systems engineer. With that in mind now, the first three speakers. And I'm going to introduce a little bit more depth for the speakers as I call them each up. But I have the privilege and honor to have a chance to listen to Eric Gebhardt. Again, Eric is GE's Chief Technology Officer. He's the Vice President of Engineering in GE's Gas and Oil. He leads a team of approximately 7,000 people. And with his role and responsibilities, he is also expected to touch GE's operating divisions and integrate its technologies for business objectives. So with that in mind, Eric?
Okay, thank you, John. Just jump down here.
Yeah.
So I was assuming I would hit that and move forward.
Maybe he has to,
Yeah.
in the back, he has to bring it up.
Nick's going to have it there.
There we
in
go.
chat.
Perfect.
There we go.
Perfect. Well, thank you very much, John, and it's great to be here today. I'm going to be talking about our oil and gas business, which is a little different than maybe some of the propulsion and the aviation side, but give an in-depth discussion on what we do around systems engineering. And when we look at our oil and gas business, it really cuts across the whole spectrum of the oil and gas industry, from the drilling side, where we do the onshore drilling, as well as the offshore drill ships, where we might be 7,000 feet of water, drill into the ground for another 30,000 feet beyond that in order to reach the oil deposits in the Gulf of Mexico, other places like that, and a large blowout preventers, other equipment with that, as well as the production side, both onshore and offshore again, where we have artificial lift technologies. We have what are called trees to do the pressure control and flow control around the oil production. We also do, once the oil or the natural gas reaches a facility, we do liquid natural gas facilities, turbo machinery that do the compression to liquefy the natural gas, as well as on the oil side, we make many of the large equipment around the oil refineries in that area also. So a full spectrum across here, as well as on the pipelines, we do the compression and inspection of pipelines across various different areas also. So some pretty large systems built within that. And what also makes it complex is that it's not built from scratch. So it's built up of a large number of acquisitions that have been made over a short period of time. GE stepped into the oil and gas space about 20 years ago with the turbo machinery, which was a close adjacency to what we were doing in the power generation side. But then starting in about 2008, we spent about $14 billion over a short period of time to make a large number of acquisitions to get into drilling, the production, further into the liquid natural gas space, as well as into the artificial lift space with electric submersible pumps, rod lift pumps, other things to pull the oil, help pull the oil out of the ground. So a large number of things that have to be integrated into larger and larger systems. So it's not greenfield, it's more of a brownfield that we really have to work with across this. So it makes it a little bit more challenging on that. So just a couple of the products and the areas that we work across here in this space. We kind of break it down into segments, but even across the segments, we have a lot of work across there to make sure we have common controls, we have software, we have mechanical systems, electrical systems across these spaces. And even looking broader than that, we also want to pull in from other areas of GE. So if we think about our turbo machinery equipment, many of the pieces of equipment we use come from our aviation group, where we use aeroderivative technology for liquefactions in that area, or power generation. We also pull from the power and water side of our business for some of the larger power generation equipment there. We even pull from our healthcare division, because much of our inspection technologies that we have as part of this team, we take an X-ray machine, a computed tomography, we jack up the dosage there, and we go ahead and shoot it through metal in order to do the inspections on a lot of the technology that we have there. And then, we lean into our global research centers for the technologies for metallurgy, materials, software, those kinds of areas there as we go around here. Now, what do we consider a system? And this is just one example of the systems that we deal with. So this is a subsea production system. And what this shows is that there's 3 different types of systems depending on the depth of the water. If you're doing things that are less than 1,000 feet to 2,000 feet, you would do a shallow water system where you may attach the rig, may actually be attached to the ground, either a flexible compliant system, or you could have a rigid system there. Then you might go in some of the deeper water up to about 5,000, 7,000 feet. You might use a tension leg platform type of system there. And then as you move farther and farther out, our deepest systems that we do today might be 12,000 feet deep in the Gulf of Mexico. And these would be off of drill ships, production ships that we would do this off of, floating production, storage, and offloading type of technology. And as we make each one of these steps out, we tend to put more and more of the technology subsea, because the cost of putting more weight and more size up on top of those platforms is very expensive. So you want to put more and more subsea in that area there. And to give some perspective, if you look at the yellow kind of features on the left-hand side, those might be 20, 30 tons of material on those. You get to the ones in the middle there, the larger ones there might be a couple hundred tons. You look at the ones on the right here, might be 1,000 tons worth of material put down there. And they'll have complete control systems, flow systems, all below there. And what we're moving to now, as we continue to do this, we have to start developing systems that would be full production facilities subsea. And that's our next challenge that we're working towards, where when we start looking at Arctic technologies, north of Russia, even North Pole areas like that, we won't be able to have platforms because of the ice that comes in there. You're not going to have the ability to have that. So today we're working on technologies where we'll be able to have full production systems subsea up to 500 kilometers offshore. So now we have to have the whole system figured out, where we have to have the electrical network, we have to have the flow network, we have to have the flow insurance, and all the technology subsea. And even beyond that, in many cases in these areas, we'll have to have subsea boosting, subsea separation, we'll have to have compression technology and reinjection technology, because a lot of water gets produced with the oil when it's being produced, and you have to reinject that back in. So talk about 100 megawatt systems, 500 kilometers offshore, in depths of up to 3,000 feet. So really have to think through the overall system dynamics, how to put that together. And walking around this here, if we look at this, we have to really have the high-level trade-offs figured out pretty quickly, where We can invest more in separation technology where you would separate the gas from the liquids and then compress the gases, pump the liquids, or develop more where you could have wet gas compression or even multi-phase compression, depending on which level of technology we really want to work on in this area. Come up with the right trade-offs, invest in the right areas, because we want to make sure that we have the optimal solutions for our customers when we start walking through this. And also the trade-offs between what do we have to solve mechanically, what can we solve through better diagnostics, what can we solve through better control across the spectrum here. So a lot of system-level thinking goes in to make sure we have the right solutions for our customers. Now, as I was mentioning earlier, a lot of this is either across businesses, across GE, or acquisitions. Yes?
Slow you up here, but is the drill then is on the seabed floor?
This is production. This is the production side. So on the drilling side, you would actually have the drill ship. You would drop it down through the drill pipe. You would put it down into the ground and then start drilling there. So on some of our offshore, I was just on a drill ship a couple of weeks ago out in the Gulf of Mexico. We were in 7,200 feet of water, and we're going to drill another 31,000 feet beyond that. And so you start drilling. Once you get to a certain depth, you then place a blowout preventer on there in order to contain all the pressures. Start re-drilling through the blowout preventer. Once that's done, you would seal it off. You would pull that off, and you would drop this tree, one of these trees, one of the smaller ones. Let me see if I got a pointer here. Yeah, so that would be a tree, or that would be a tree, or something like that would be a tree, depending on the size. You put that on top, and then you produce from there. So that would be a set of valves and a set of flow meters that you would have on that tree. That make sense? Okay. And so in order to have the team work together, so the 5 different segments that I had talked about earlier are each of the verticals that we would have here, each one trying to specialize their equipment to serve the customers in each of those areas. And then we have what we call horizontals that would cut across, a systems team to try to pull the systems together across there so that we meet the needs of that segment, but also drive commonality, drive standards, drive modularity across there. Systems engineering, software and analytics, advanced technologies where we may be sharing metallurgy, polymer technology, analytic technology across there. And then within that systems line from earlier there, we would also have another matrix within that. And this is to drive really the constructive conflict that's necessary. So within the systems team, we would have architects, similar to what you would have in software. So we would have a controls architect that's trying to drive the best controls architecture across GE oil and gas, and even at a higher level across GE. Software architects, mechanical, electrical, electronics. But then we would also have individuals that want the best solution for turbo machinery, the best solution for downstream, which is petrochemical and the chemical side of the business, to come up with the right solutions across here. Because if you let either side kind of dominate, then you wind up either having segments that can't work across each other and can't leverage technology, or you wind up having common solutions that really doesn't fit the purpose for anybody across there. So you have to be able to develop this kind of constructive conflict. It's a journey. Every year we wind up acquiring more and more companies. When we go across here, we have to fit them in. We have to figure out how it fits in. And we step into new spaces all the time across here. But this is kind of the roadmap we've followed to go from pretty much double the size of the business in the last 5 years, to go from $10 billion to $20 billion, bringing in new technology, bringing in new systems, bringing in new cultures to try to drive us forward in the right direction. So with that, I'll turn it back over to John.
Thank you, Eric. I'd now like to introduce David Long. For over 20 years, David is focused on enabling and applying advanced model-based systems engineering and model-based engineering concepts. As I had mentioned, David is president of the International Council on Systems Engineering, which is a 9,000-member professional systems engineering group. And lastly, David is the founder and the president of Vitec Corporation, where he developed and commercialized a tool that's called CORE, which is a leading systems engineering software environment. David?
Thanks, John. And by the way, I forgot to give you an update on Incosi last night. We're now over 10,000. So we crossed the magic number.
Bravo.
So I've got to keep John back briefed on all the progress that we make. When I talk about systems engineering, I generally talk about engineering. The reason I do that is I find far more people practice systems engineering than ever consider themselves systems engineers. Okay? Part of that is because systems engineering is often practiced under many different names. Also, many of the people who do systems work consider themselves first and foremost an automotive engineer who's doing a systems perspective, or an electrical engineer who's working at the systems level. Today, however, I'm going to focus on the systems engineer for some very specific reasons. Okay. Let's start by talking about the good old days. Now, we can debate how good they are and we can debate how old they are, but it's certainly not the present. And you can talk in an era of electromechanical systems. Relatively complex for the time, certainly complicated, complex, but in large part, we were able to specify standalone greenfield, not brownfield, greenfield systems that were meant to do one thing and do one thing very, very well. And when we did that, it was often simple enough that you could have a customer and a systems engineer define top-down what this system must do, write the specs, provide the details out to the specialty engineers, and go on our happy way. This is how we got radar systems and all sorts of aircraft and other wonderful systems. But those good old days are definitely old. The new reality is completely different. First off, we're not doing much greenfield engineering, if any at all. It's all brownfield. We're deploying into existing environments. If you're deploying a new storage capacity onto the electrical grid, you're going into an existing electrical grid. You don't get to build a new electrical grid in most cases. We see the rise of software. Software is much bigger now. Now, the software engineers will tell you that's because they have to fix all of our problems, but it's certainly the glue. You see an explosion in complexity. And so no longer do we see any sort of top-down drive. In fact, we see the need to bring the insights from these disciplines, these domains together in a far more collaborative and integrative sense. The other thing is we see very, very rapid innovations in these supporting technologies. Okay? What's happening in battery technology, what's happening in turbine technology, what's happening in materials. Those innovations we're trying to feed into better and better systems answers. And we're trying to figure out how to do that today. The old top-down system won't work. So it gets us to the integration challenge. Now, most of the times when we talk about systems engineering and integration, we focus on the so-called system of interest. What is it I'm trying to build? Maybe it's a product, maybe it's a service, maybe it's an enterprise. But that, in fact, is only one of three primary systems that we deal with. Okay, we also deal with the environment that we're deploying into. That's its own system. The one I want to talk about is the system that brings the system of interest into being. Okay, that's a design system. It's a manufacturing system. It's all that. But the key thing is for that system that brings the system of interest into being, all these same integration issues exist that Eric just talked about, that John talked about at the start. The design team, the manufacturing system, they're all built up of parts. You need those parts working together in an integrated way to deliver the best possible results. And that's why I want to talk about the systems engineer and their role in doing that as opposed to systems engineering. There are natural disconnects anytime you bring a team together, okay? Let's do a quick experiment. And Don, you're out of this because you heard this experiment at the Incosi International Symposium. Close your eyes. Small audience, I can see if you're cheating or not. I want you to picture a dog in a yard. You got that image? Okay, open your eyes. How many people's yards had fences around them? Okay, that's good. How many of you pictured a yard that was about this long, a glass tube, and it was filled with flying dog beer. Okay? Courtesy to Scott MacArthur for that example. That is an example of the wonderful power of the English language, how diverse it can be and how badly it can mislead us. All right, that's fine, David, but that was a completely concocted example that would never happen in the real world. A month ago, I went to Cincinnati to speak at a SimData event. Product lifecycle management, we were talking about model-based systems engineering. Theoretically, everybody in that room would know what model-based systems engineering was. We got to the end of the day, I heard several other speakers present. I spoke. We got to the bar in the evening. We were trying to digest what we heard, and we realized that when we were talking about model-based systems engineering and systems models, some of us were talking about very abstract, low-fidelity models early in the cycle. Others were talking at a physics-based level, and those two are this far apart. And we couldn't figure out why we were talking past one another. That's really problematic when you're trying to build a system. How about at a very detailed level? John Wade and I were at lunch. We were talking about an example where they had to build to a 48-volt bus. That's pretty clear, right? Unless half the team builds to a positive bus and half the team builds to a negative. All right? Or let's pick on NASA. Sorry, Ray. How many systems are lost because of units errors? Okay, it's a very, very small detail, but it's a very, very important detail. These are all systems issues that exist at the design team or the production of the system of interest level. Systems engineer needs to play a key role in solving that. The hidden complexities of engineering systems, okay? We often in systems engineering talk about what is above the so-called waterline. Certainly everybody knows the requirements, the capabilities that we're interested in fulfilling. We certainly talk about the parts, the components, how they interact, the behaviors they're going to show. And traditionally, we're interested in specifications, the detailed statements that instruct the next level engineers what it is they're to build. Okay? It's the stuff below the waterline that will get us in trouble. And it's the systems engineer or those doing systems engineering that need to deal with decisions, risks, performance, traceability, constraints, and all that. And it's not just complex, it's interrelated. For me, the analogy is much like a spider web. If you grab a hold of a spider web and pull, the entire web moves. You can't reach in and pull one parameter, as was described, and get just that parameter to shift. The entire system pulls with it as you're doing those trade-offs. Okay? Worse than that, you can't do it late. We so often talk about security these days. Okay? Security is not something that you can bolt onto a system at the end. If we're talking about autonomous vehicles, going down the highway and I'm in one of those, I'm very, very concerned about how the security is around that vehicle control. I was sitting in New York doing a system software conference, and it was humorous because no one got hurt. But the news story of the day was how they had lost about a quarter of their New York network because somebody had figured out how to come into the network through the RF controls on TV and take over the network. Not something you would have ever thought about, not something that you're going to protect by bolting on top. You've got to engineer that in from the very beginning. Look at all these specialties that we have to concern ourselves, all these members of the team, all these connection points, not just between parts, but between team members. Is a safety engineer, a security engineer, a test engineer, a manufacturability specialist, a software specialist, are they all going to be able to talk to one another? The answer is no. Okay? There is no one language that's going to unify that team. So what I'd like to talk about, what I like to believe, is the systems engineer is part of that glue. This is a very recent chart. Format is different because I've stolen it explicitly from the Systems Engineering Research Center and the Helix project. The Helix project is a study to try to discover the so-called DNA of a systems engineer. What is a systems engineer? What makes them different? What makes them good? What value do they bring? And this is based on the first year of data. It was just out briefed last week. In particular, note the paradoxical mindset. It's really kind of unique. Systems engineers Both do big picture thinking and attention to detail. They're able to hold that entire picture of what is it the customer is asking us to achieve, while at the same time ensuring that we don't make a units error. Yeah, it's pretty challenging. They work both strategic and tactical, both analytic and synthetic, building things back up, courageous and humble. They're able to deliver truth to power, okay? And yet take a step to the background and give credit to others. Be both methodical, follow processes, and be creative, be inspirational. This is critical in bringing a systems engineering integration force to this kind of team. So to me, if we're going to deal with complexity, if we're going to solve these classes of problems, you cannot unify these kinds of teams with one common language. It's a fool's errand. However, you do have to deal with all of the concerns to make sure that security is handled on day one. It's part of the whole, it's a holistic part of the architecture. That you bring the latest insights from software, you bring the latest insights from the implementation technologies, that we can continue to make the most out of our solutions. And the answer, therefore, is really to bring the systems engineer to the middle. Not that the systems engineer is the most important person on that team. They're certainly not the most powerful one. Any systems engineer will tell you that. But they are a key connector, a key integrator. Ultimately, okay, the purpose of systems engineering is not to deliver specifications in the old days. It's not to deliver models in the new days. I'm a model-based guy. It's not actually even to deliver the system of interest. It's to deliver the business value that the customer is seeking, and we do that by delivering the system of interest in the best possible way. This connection point is one of those best possible ways as the systems integrator of the engineering team. John, I'll turn it back over to you.
Thank you, David. The last presenter of in this first set, I'd like to introduce Paul Nielsen. As I had mentioned before, Paul is the director and CEO of Carnegie Mellon's University Software Engineering Institute. Many times people just recognize that as the three letters SEI. Also, Paul served in the Air Force and retired as a Major General. His final assignment was that Paul was the commander of the Air Force Research Laboratory and the Technology Executive Officer for the entire Air Force. So it's my honor to introduce you to Paul, and I'm sure you're going to find this very interesting.
Thank you so much. How's everybody doing today? One demographic fact you didn't ask that I'm curious about, is anybody in the crowd from another country? Anybody here internationally? That's interesting. Well, not really. Yeah. Not really, once upon a time. That's interesting because AIAA conferences do draw a sort of big crowd of international people sometimes. And it turns out that many of the engineering challenges we face these days are further complicated because parts are built in many countries, right. There's engineering teams from many countries, and that's sometimes a little hard for us all. Now, sometimes when I talk about myself in my own intro, I say, you know, all of us are complex people, and we all sometimes are paradoxical. I went to the Air Force Academy, and I was an Air Force officer, but I was never a pilot. I was always an engineer and researcher. I work at Carnegie Mellon University, but I'm not on the faculty. I'm in a unit that's kind of a research unit that works for the government. And I'm at a place called the Software Engineering Institute, and I'm not a software engineer. So we are all paradoxical creatures, aren't we? And I started off as a physicist, ended up being more of a double E in the Air Force, and then became a system engineer, I hope a reasonably good one. And then, you know, took that wrong turn and became a manager and a bureaucrat. And hopefully, again, I was a good one, but who knows? You'd have to ask people that worked for me. I get really excited about this whole business, and especially about the increasing size and complexity of the systems that we're building. Because I think that's one of the real challenges of our generation, is we're building systems that are more complex. We're building systems that do things that were never done before. That's the real excitement for me. Let's see if I can get this thing to work now. There we go. So as we look out there, systems are becoming amazingly more complex. They're not doing that because we have a thirst for complexity. We're doing that because we have a thirst to satisfy consumers' needs, government needs, other kinds of problems. And the edge that we can bring sometimes is by bringing systems that are more complex to solve those problems. Some of the systems we build are really complex, but they look pretty simple. You know, one of the great examples of that is, man, you buy one of those iPads or iPhones or an Android phone, and the user interface is so great, they're so simple. But let me tell you, beneath the hood, there's a lot of complexity. And a lot of great engineers, software, system, double E's, spent a lot of time building that operating system so that to you, the user, it seemed almost intuitive. Furthermore, they built it in a way so that you could add these apps without having to retest the whole system, without affecting the security of the whole system in a very easy way. And when you think of that, this is an amazing design. We need more designs like that in the military as we go forward. Now, not only are the systems becoming more complex, but they're really becoming much more interconnected. This is another hallmark of our time. We're trying to connect more things to more things. I read the other day that as at the end of 2012, there were about 9 billion devices connected to the internet. And by 2020, we expect 28 billion devices connected to the internet. There was a time when the internet was a place for people to communicate from desktop to desktop, mainframe to mainframe. But now we've got cars, refrigerators, you know, all kinds of things communicating over the internet. And it's not just, again, for fun, it's because of useful function. We're finding that there's reasons to do this. It makes our lives better. It makes us able to interact with other people in a different way. And so this increased interconnection, though, brings a lot of challenges, as was already mentioned. If you think that every time you have a node, you're adding some complexity, as we interconnect 29 billion things, we're going to have a heck of a lot of complexity in there. I might add one aside. When in the Air Force, toward my latter time, we were trying to figure out how big should a program office be to manage a system. And the answer came, you can't tell by that. You can't tell by how much money they have. You can't tell by what kind of program. One of the biggest determinants was how many organizations they have to interface with. Because the more organizations they have to interface, the more complex their job ends up being often. It gets back to the people side of software and systems engineering, right? Yeah. So we're seeing things become much more interconnected. We're going to have cars that are interconnected on the highways. If we get to autonomous vehicles, there's going to be a certain amount of connection between them, hopefully done very safely. We're finding people now sometimes have devices inside of them that are interconnected by Bluetooth or other things, whether they're insulin pumps or other kind of devices that you can set Bluetooth. You want to make sure those are secure, right? Now, the final intro thing I want to say is that these systems are interfacing with humans in new and novel ways. Many years ago, you know, in the 20s and 30s, the Air Force initiated a lot of research on how to best present data to a pilot so a pilot could fly an airplane with all the different things that are happening on there. And that's one of the early phases of human system interaction and integration that was done. Now, as you know, we not only have airplanes that have to interface with people well, but even complex decision systems. We've started to recognize that you can't just do the silicon side of that. You got to think of the carbon-based side of that too. Because the system is not just the hardware and software, it's got the person in it too. So when we do good systems engineering now and good system integration, we have to think of how the person plays in that, how the ultimate user plays in that if we want to do this design well. And fortunately, we get to take advantage of the best of both of those kind of intelligences, silicon and carbon. And good design thinks about that as they go forward. Okay. So one thing I'm going to say, and this might be a little controversial, but that nowadays it seems like software is really at the heart of many of these systems. In planes like the F-35, they say 85% of the functionality is represented in software. In a modern car, could have 100 million lines of code in the car right now. We got less than I thought we were going to have here, but if we have altogether 40 or so people in this room right now, and everybody's got a smartphone with them, I bet, and maybe some people have a pad with them too, a tablet of some sort. We have 500 million to 1 billion lines of software in this room right now working. And even as we're sort of oblivious to that, those phones are checking into the cell, making sure the cell's there, checking into your email, downloading stuff, doing all kinds of functions. That's all being done by software. The interconnection of many of these systems now is being done by software. Sometimes now the integrated circuits themselves, especially the DRAM, those are just commodity devices. What really makes these systems come to life and give new functionality that users want is the unique way that software is built. Certainly software interconnecting with physical systems, but the way that software is built. So it's very important now that when we do system integration, we have some understanding of software, how software works, and what the risks are in developing software. I believe that one of the most important things right now in the complexity world is the whole idea of architecture. Software architects, system architects, architects of all kind. Because architects help you look at systems in simpler ways sometimes. And they also give you different views to look at the system that are useful. Okay? So just as a doctor would look at your body, first he might look at you, how you're feeling, but then he takes an x-ray, then he looks at your nervous system, then he might look at your digestive system. Just as he gets all those different views of your body, great architects help give different views of the system that you're building and really help to work to tame complexity. Now, there's no single architecture that's right for all systems. I think we all know that. And so what you have to do as a good system architect or a good software architect is really not only understand what you're trying to do, in the system, but try to understand what the business model or mission model is that you're ultimately trying to achieve. And so what architects have to do is blend those things and try to come up with systems that blend all of that. I think one thing that we're finding right now, talking about not building too much with greenfields, not building systems from scratch, is we have to have systems that can evolve well. Systems that can have long lives in their operational phase and can continue to evolve and gain functionality. To do that, you have to architect right, otherwise you get into a quagmire of system tests and other things as you go forward. We're finding that in the software world, but I believe this is true in the hardware world too, quality gets even more important at scale. As you build larger and larger systems, it's more important that you build those systems correct in the first place, or else you'll get into a never-ending cycle of test and repair, or deliver and fail, which is even worse. We're finding in the software world, a lot of great software companies will deliver software to the field with 1 defect per 1,000 lines of code. And you can use function points or other things if you want to do that, but roughly that's a measure, 1 defect per 1,000 lines of code delivered to the field after all their tests, okay? If you're building a system that's a 10 million line system, that means you're delivering a lot of defects to the field. And ultimately, your companies, people are going to find those, and you're going to have to fix them, and it's going to cost you money, it's going to take you time, it's going to take your attention. Well, what about when you build systems that are even larger than that? About 8 years ago, the Army asked us to do a study on the ultra-large-scale systems of the future. So what if we have to build 1 billion lines of code of software for a system? And we thought that was kind of maybe unusual. We're not building systems that large right now for the most part. But then we thought about it. We actually are. We already have systems like that. Because through the interconnections, we've got a lot of software talking to a lot of software. Okay? So we went back to the Army on that and said, look, your big point isn't lines of code, it's interconnectivity, it's other measures of complexity. And so we've looked at that. And as we look at these larger and larger systems, we find that is many more cases where emergent behavior can start to show itself. And sometimes that comes because of flaws that are designed in the system, even as far back as the requirements phase. So you have to make sure you've got good requirements even as you go into that, okay? It was mentioned that you can't patch cybersecurity in at the end, or any kind of security into the end of a system. My gosh, don't we know that? Most of the business of my organization is actually in cybersecurity right now. And we actually had a paper just pulled from a conference. Anybody up here know this? So we were presenting a paper at a Black Hat conference, cybersecurity people, that some research a couple of our people did that broke Tor. Tor is a circuit to browse the internet anonymously. And we were able to de-anonymize that, which is a big thing, except the government wouldn't let us present the paper. So don't use Tor if you're trying to be anonymous. If you're trying to do something bad on the internet, just don't. That's the best thing, just don't, because somehow people will find you. The big key with cybersecurity is now we're learning that security plays throughout the darn life cycle of all systems. Throughout the life cycle. Now that we don't manufacture all our parts in the United States, we've even got to worry much more about the supply chain. And there's big cybersecurity hacks that have occurred when the BIOS in computer systems was compromised at the source. So that even if your system had all the nice firewalls on it and everything else, that system was reporting out stuff to another country. Okay? So we've detected that. So the supply chain's good, really important. Then coding itself is important, and there's ways to code more securely, just as there are ways to build hardware with a more secure purpose. The key is to do things right and not to do common errors that many software people do. As you go through the system, of course, if you architect the system right, you're going to have more security. If you architect the system correctly and implement that, you'll be able to maintain security on your system as you go through the life development cycle of it. We believe that more and more mission assurance and resiliency are bigger topics when you have very complex systems, because even after you've done everything you can, there's going to be defects, there's going to be vulnerabilities in your system. So you better build a system that's considered the risk and that's tried to make it so it's not so brittle that the first time there's an error, it breaks or it's completely open and hacked. Resiliency is a very important concept in all systems, hardware, software, personal, everything, right? And resiliency isn't only for that black hat that's trying to break into your system. It can be because of natural disasters. You know, the government at times has spent a lot of money on resiliency as far as the continuity of operations. What do they do if the White House is targeted? What do they do if the Pentagon's gone? How do they continue operations? Banks around the country could worry about this a lot more than they used to after 9/11. What if your main headquarters is attacked? How do you continue your operations? If you can't, are you out of business if you're down for a week? Think about that, okay? Finally, we believe that virtual integration can really help. And it was talked a little bit about some of these new modeling and simulation systems. In the past, modeling and sim was often used for other systems. So we were using software and software-based systems to model hardware systems. But now we're getting much better at modeling software systems themselves. And so as complex as systems are, you don't want to necessarily build, integrate, test, and find out you got a lot of problems. What you want to do is integrate, at least virtually, to kind of explore some of your problems and explore the space that you're operating in, and then build and test. And there's lots of things being developed right now that can really help in that regard. Finally, I wanted to talk about the architecting for the testing of extensible systems of systems. More and more, since we're adding stuff to existing systems, almost like adding apps to the system, we need to make sure we got architectures that will allow that. The government and the DoD is really worried about, okay, if I've got a system and now a system and I add one more function to that from the outside, do I have to retest the whole system? Do I have to go through regression tests on the whole thing? Because that can kill the development cycle. So we can architect systems in a way that you don't have to test the whole system, just the new interface, just the edge material that's being added. I never give a talk without reminding people that as much as we talk about technology and as much as we talk about process, in the end, it's all about people. And so we live in a world where the technology, everything else is changing so fast that we got to make sure our people keep up with that. So one of the major functions of all of us is to make sure our people are given current information, given current education, get OJT and other things to keep up their skills, because the tech world is changing so fast. More and more I'm finding it's not just the technical people that need that, it's also the managers. It's also the board members, people that are involved in assessing the risk of organizations. Target, what did they think about the risk of their software systems? You know, Target, they say, is going to end up paying $8 billion for those errors that happened before Christmas this year. In remediation cost, in legal cost, in cost to provide credit checking systems for all the people that were affected. That doesn't even mention the reputational damage they have. $8 billion. We know companies at SCI that have gone out of business because of cybersecurity problems. So we need to make sure everybody kind of keeps up with all the challenges that are in this system. So to get the system behaviors we want, I believe you have to focus on architecture more, that in the whole life cycle you have to make sure you're concentrating on quality of software and the hardware throughout that thing, that we have to think about the whole ideas of risk, mission assurance, and resiliency, that we may be able to use some of the more modern techniques of virtual integration and virtual tests to explore architecture early in the system, and that we need to, for sure, invest in our workforce across the board. That's what I've got for you today. Thank you.
Thank you, Neil.
You bet.
Okay, so here's a notice. In a little bit, I'm going to ask whether you have any questions. By the way, has anyone got a question right now? Because I can start the questioning and give you a moment. Let me ask something that should fall under what I would call career mentoring for us. It's the rare case where someone isn't interested that I've been interacting with on moving up in their organization or making some more money. So I would ask the panel, and John, wait, I'm going to start with you, but I'm going to go around. I'm interested in how has your career been advanced from your viewpoint by your ability to see the big picture and the interrelationship between parts and how that gets in the way of an organization's objective?
So my experience has been, in terms of leadership, that it isn't something that's assigned to you. There's an opportunity or there's a gap or there's a hole in the organization, and so you sort of rise to fill it. And I think that in the area of systems, there are few who are able to sort of see those gaps. And so people who in the organization who have that view or that vision have an opportunity. And so it's really up to people to take that opportunity or to not take that opportunity. And generally, those types of roles lead to more responsibility and they lead to sort of a broader picture. So it isn't like it's a one-step process and then you're done. It's that practice and behavior sort of strengthens those muscles that cause you to do that again, and again. And so you get a virtuous cycle where you sort of move through the organization, that behavior.
Well, thank you, John. Other thoughts? Neil?
Well, Paul.
Oh,
That's okay.
Paul, I'm sorry.
That's okay. So, I had a time in my career, kind of at almost the 10-year point, where I was just finishing up a PhD at Livermore and working inside the laser fusion program there as I was doing it. And then I went to the NRO building satellites. And in both cases, what I saw was that, gosh, even when you're technically deep and doing something that's very important, you have to have the big picture to know how you fit inside that. At Livermore, we were working, at that point I was really working at the nano level trying to get a PhD, but we were trying to build this amazing laser fusion system, with 190, the one they have now with 196 arms and half the timing has to be right. You can't do that without a system view. Similarly, when I went to the National Reconnaissance Office to build satellites, the king, in a way, in a satellite office is often the person designing the payload. But it turns out the satellite doesn't work if the bus doesn't work, if the ground station doesn't work, if the users don't get the information or can't use the information. So there it kind of quickly became obvious to us how important it is to have a real systems view. And I don't know if it's always system engineering, because that can be a little more formally defined sometimes, but at least people have to have a systems view.
Thank you.
So I'll jump in with a couple of pieces of advice here. The first is always do what you love. And I've always been drawn to systems and those types of things. And I can remember two pieces of career advice that I got. One early in my career, probably 5-6 years in my career, and the HR person, my manager, came up to me and said, if you ever want a career in GE, you have to get out of engineering. And I was shocked, I was appalled, I couldn't believe it. And I said, but I love engineering, and I want to stay in engineering. So I stayed in engineering. And then a couple of years later, and my career was, I started out doing controls and operations of power plants. Started off with coal-fired power plants, combined cycle power plants, nuclear power plants, moved into wind, moved into smart grid, and moved across there. And at one of the points, about 10 years in, HR came up to me again and said, your career makes absolutely no sense to anybody because you keep jumping around between all these technologies. I said, but that's what excites me and what draws me to it. Probably 5 years later, came back and said, you have the perfect background for this great opportunity. And so do what you love, and systems engineering, you have to be deep in something, but systems engineering gives you a different perspective, allows you to move in your career in different ways, and like I said, do what you love.
Thanks, Eric. Other thoughts?
I think that in my career, the big factor was being able to move around, but also curiosity about how things work. And I think that curiosity led me into positions that broadened my understanding and gave me that system perspective. I think one of the things that helped me was having had a minor degree in psychology. And I say that because moving into these different jobs, you have to deal with different people with different perspectives.
Yes.
Sometimes different behaviors. Moving from manufacturing to design was a big change in behaviors. And you need to really learn how people tick, I think, to be a good system engineer.
Thank you, Don. Thoughts?
I think in my career, it was just in the area I worked in, at the interface. I pushed on the interface, and which led me over across to that system, and kind of spidered out and grew organically into more system perspective.
Thanks, Rick.
I appreciate the fact that we're primarily talking about the systems perspective as opposed to systems engineering. Oftentimes we focus in on the engineering, which is the interventional side of it. And in John, in this case, I think it's the systems perspective that's more important. The thing I would call out is when you look at what distinguishes the systems perspective, oftentimes in business language, that's then called seeing the whole picture, having vision, et cetera, things that lead to general business leaders. And it's a matter of what you then use, what you're using that skill set for. The one generic comment I will make, because I have seen people get in trouble with this, is you can argue nature versus nurture in terms of systems perspective. I do tend to think that most people have it at a younger age, and Western education does a great job of driving it out of us, as it trains us for very good reasons to be specialists in specific technologies. If not, we wouldn't have many of the great advances that we do. But it's something that can be trained back in. However, once you have it, you need to be careful that to realize that most people are not trained to think the way that you think. And it can get you in that same mismatch and into trouble.
Any other thoughts, Keith, from what you've heard? Are there questions from the audience? Yeah.
Probably
Yeah,
best,
please
probably
do.
best.
Please do.
I want to address the question when you don't risk in a broad sense. And I have some specific questions, and I also have a very broad question. At the risk of not talking out the panel for the rest of the day, which happened in the session this morning, I'll hold that to the end.
Okay.
That way we'll keep it going. But in the area of risk, if I can use an example. First of all, my personal bias has been, as a system engineer, that risk management is an integral part of the system process. And it needs to be, at every step of the way, integrated into the life cycle methodology and evaluation. And as David explained earlier about security, you can't bolt it on at the end of the process of the life cycle. You have to pull it. It's the same thing with risk. So in a system view that I would have, I would say that the systems process focuses on how to do the thing right, and the risk process looks at how might it not be right, how might it fail, and so on. And those two have to constantly interact with each other. So I want to ask Eric, if you don't mind, on the very elegant presentation you made on deep sea drilling and so on. You mentioned blow-up preventers that are placed. Of course, we all trigger. We all recall what happened in 2010. So my question on that specifically is, what do you feel in the oil and gas industry? What can we learn so that we don't have these kind of black swan situations, which are devastating and costly, as we all know. We had a shutdown, 2.5, 3 years ago. Similar cases have happened in the space program. You know, Challenger, 2.5, 3 years of shutdown in the space program. Same thing that was wrong. It seems to be such a difficult thing to focus on those critical risk areas that are low in probability but so high in consequence that they shouldn't be ignored. The classic 1 by 5 in the risk management matrix, right? Now, back to your business, can you comment a little bit about how you adapted and overcome that situation?
Yeah, so that was a tragic event that occurred. It was not with GE equipment. Just feel like need to put that out there. But everyone should always learn from anything that happens in their industry and make sure you're taking best practices. And when we look at it, there were several things that were said could have happened when that occurred. That either the casing had come up and not allowed it to shear, it was an off-centered pipe, or it could have been that there was a knuckle. So there are tool joints when you're drilling that go in there, and some blowout preventers cannot cut through tool joints, was kind of the standard at that point. And so what we did as GE is we looked at all of these things and made sure that our equipment could handle any of these types of consequences. So we have casing shear rams that can cut through casings. We also have equipment that can cut through the knuckles that are in there. We've proved that. We were the first in the industry to prove that, to make sure that we can cut through the knuckles if the knuckles happen to be in there. And we also have the capability to go ahead in an off-centered pipe. We actually have almost bull horns that pull it back in and can shear through that. So we look at all the events that could have happened in that and make sure. On top of that, some of the things we saw that had happened, the fact that the industry did not know whether the rams had actually actuated or not. There were no indicators, there was no feedback loops on that. So we went and made sure we put the feedback loops in there to make sure that we understand the positions of the rams. Not only that, it gives you better diagnostics so that you can understand the speed at which the rams are moving during your testing, how much pressure it takes, look for wear-out mechanisms, those kinds of things. So we take these situations extremely seriously based on our background. We pulled in specialists from our nuclear division, from our aviation division. Nuclear has a practice around core damage frequency. Do a complete reliability map, look at the probability of causing core damage, work your way back from that for what you have to do. We did all of that on our blowout preventers. And we shared a lot of this with the regulators and others to make sure that we weren't keeping this, because similar to aviation or nuclear, the more we share this type of information, the better off everybody is around this. Yeah. So it was a tragic event. There are lots of things that are happening. And in fact, just probably 4 or 5 weeks ago, I think it's the Chemical Safety Board just issued their reports on what had happened at Macondo. And there were some other issues in there that were highlighted. I circulated that to all of the leaders on my team in that section, made sure that we're learning from those experiences too. So, these are mission critical systems that have to work. So not only does the hardware have to work, but there's also things on the human side, the carbon side, I guess was the comment that was made earlier, that there's a lot of practices that have been done on that side too to make sure that the right actions are taken, because there were several things that could have avoided this even when it was starting to occur, that could have avoided it from escalating as much as it did.
I just want to agree with you. I think one of the major functions of system engineers is to manage risk, identify risk, and then hopefully manage it. But I also think that's one of the major responsibilities of senior management, of boards, of all kinds of people. It's not an easy thing all the time, though. And sometimes even when we identify risk, we don't know what to do about managing it, or we don't take the steps to manage it.
Yeah.
Or we wish it would go away.
Yeah.
I think that's to the point. If you look at the broadcasting Challenger, and I use it for a course I teach.
Yes.
They say, we're finally getting off. We're finally doing the liftoff. It's been delayed more times than NASA would care to admit.
Yes.
And the temperature's colder than
Than we've ever done.
And then it goes. And Richard Feynman went in and he asked NASA management. He said, "So what are the probabilities of catastrophic
Individual mission
failure?"
success. Yeah.
And I think it was 1 in 10,000, or that was kind of the spec. And then he asked the engineers, and it was like 1 in 50, which turns out that was about right.
Right.
The information is usually in the system. And one of the things that I would do when it was time to sign off or whatever those big transitions was to have anonymous polling of the engineering organization. And we usually got good data. It was unpleasant data. It was painful data to see, but it was usually fairly accurate data. And if you're not willing to hear bad news, then you have to accept the consequences of those actions. And I think quite often that's where we fall apart, is we're not willing to take the pain and look at the unpleasant truth early
Yeah.
on.
I also think there's been studies to say people aren't really good at understanding risk naturally. You have to resort to numbers. You have to really get into this, you know. And I think as evidence, they say, well, look at all the people that buy a lottery ticket thinking they're going to win. You know, we don't understand risk so well, do we?
Yeah.
I would also build just a little that the modeling is great, and we need to be really good at modeling, but the physical test capabilities.
Yeah.
And one of the things that we do now is that any time that there's any kind of a near miss or anything in the entire industry, we make sure that we figure out what were the 3 or 4 scenarios that they came up with that could have caused that, take that, test it with our equipment to ensure our equipment would work in those scenarios. We try to learn as much as we can from that. And I think it's that healthy curiosity that was brought up there. You know, model it, but then prove it to make sure. So you got to think on both sides of your brain all the time to be successful in this space.
How about on this side? Thoughts? Triggered?
In our industry, I think safety is paramount. Producing things that people fly on, and we are very rigorous about our FAMICA analysis in terms of looking at systems and understanding what are the possible failure modes. And even to the point of looking at FAMICAs on top of FAMICAs from certain systems to other systems. So you're getting a cross-system FAMICA, if you will, and trying to understand what are the possible failure modes, and then looking how we might mitigate those. I think we do a fairly good job of that.
To make sure, share with everyone, FAMICA is short for?
Failure modes, effects, cause analysis.
Okay. And in one form or another, it always comes down to take a node, and what happens if some unintended consequence happens to that node and propagates through the rest. It's interesting, back to this notion of the context of nodes, connections, and what's that big picture. Greg or David, anything? Other questions from the audience? Yes, sir, please.
So the title of this session is Ensuring Critical System Behavior. So my question is on that topic. Particularly as these systems get larger and more complicated, and we start to move to concepts like distributed control, or at least noticing some form of interactivity at various places around these systems, how would you go about trying to assure system behavior? You can only do so much testing of every single possible scenario.
Right.
Because you never run it.
Can't test them all.
Right.
You can't even test every possible interaction between all these devices. If you look at embedded systems, we have a whole history of how to test embedded systems. We do things like test for race conditions. We still come up with situations where the system, the embedded controller doesn't behave as we expect. So how do we go about taking that leap from single embedded devices to thousands, hundreds of thousands, millions of thousands of embedded devices?
Very good, thank you. Gentlemen, any thoughts?
Well, I spoke a little bit originally about, in my talk, a little bit about architecture being important, because with architecture, you can sometimes decompose a problem that's really hard into a little bit simpler problem, and maybe take that n factorial problem into something less by having fewer interfaces the way you design. But in addition, when we build these really large systems, we know there's going to be problems. And so you have to start looking at the risk, as we just talked about, but also the resiliency of the system. Can you build a system so that even when it has problems, it can at least be safe, or maybe even continue its mission? I mean, the human body is a complex system. We get an illness, we don't shut down in most cases, right? We don't get the blue screen of death on our face. We sort of continue on, and we kind of isolate the problem to certain systems, and even while our body's fighting the disease, we kind of go on and do other things. Cities are complex, right? And cities, they have a fire in a city, the whole city doesn't shut down. They learned how to isolate, how to reroute, how to do other things. We have to learn some lessons, I think, from biology and from city planners and those kind of architects on how to build systems that can continue to work even when there's some problems inside of them.
Yeah, and I would build off of Paul's comments that architecture is so important, and also having an architectural philosophy.
Yeah.
How do you approach it? Do you use the Purdue model with L0, L1, L2, L3 model to go ahead and separate protection from control, local versus supervisory? Because those are critical things to walk through.
Right.
How do you protect the components but also protect the system? And sometimes you have to sacrifice a component in order to protect the system. And that has to be clearly laid out, and those aren't easy discussions. Where, for instance, right, if you wind up getting too much load coming in from the driver, you might have to sacrifice the generator because you don't want to pop the generator breaker and go to uncontrolled overspeed. You have to make sure you're having those types of discussions around what portion and how do you protect the system as well as the individuals that are around that, and how do you walk through it. And I think also, as you walk through your system design, understanding where do you want to distribute functionality is so important, because many times people look at whatever their subsystem or component is, and it's the master of the universe. And so if you look at a control system, for instance, right, the sensors teams right now are saying we need to put some rudimentary control and signal processing in our sensor. You look at the signal processing teams, they're saying we want dumb sensors, we're going to pull control away from the control systems. Look at the control systems, they say get the signal processing out of the way, dumb sensors, and then the software teams like, Paul, I want to take over the world, right? How the architect looks at that from both a cost perspective, a reliability perspective, a safety perspective is so important, and that's where system engineering really comes in.
I would say that architecture can only take you so far, unfortunately. And if it's greenfield, great, then we can make that happen. But unfortunately with brownfield, there's limitations. And I think in that case, where you do have complex systems, you really have to instrument the system. You have to monitor the system. You have to understand when is the system safe and when it's not safe. And sometimes actually shutting it down is the best thing that you can do. You know, if you look at your laptop, you know, it's doing, what, 2 billion calculations a second, and every one is correct in every digit. And it's because it's monitoring the temperature, the voltage, you know, frequency, it's monitoring all those things. And if anything gets out of spec at all, it shuts down because it knows you don't want data corruption, you don't want your files corrupted, you don't want those sorts of things. And so sometimes you have to look at these systems and say, okay, what are the key capabilities that I have to protect at all costs? And I may have to shut other things down in order to ensure that I'm going to be able to protect those, those attributes, and then be willing to shut it down, and then compartmentalize yourself and disconnect yourself from other systems so you don't bring the entire system down. So you can have some controllable shutdowns like that rather than counting on the whole system being up. I mean, frankly, what happens if the internet goes down for 3 hours or we lose GPS for a day? What's going to happen? We've never seen that before. I don't know what's going to happen. I mean, and I think those are the kinds of challenges that we have, because it will happen at some point in time, yet we're totally unprepared because we've never seen those failures.
I think one thing that would be interesting to hear people talk about too that's in this area is, as you integrate more systems with each other, there's always a level of coupling that you're doing. And if you're loosely coupled, it's a little bit different than if you're really tightly coupled. You know, if everything has to happen exactly at a certain time, then you got more potential problems there. And if the systems are more loosely coupled so they can kind of continue to work even as they're waiting for information, you probably got a better chance.
How about on this side? Other thoughts,
I
Trigger?
think from the automotive industry where I come from, I think to John's point, the tendency is to shut the system down. The automotive industry is interesting because we're building basically 17 million commodities a year, and they're highly, highly complex. And there's a lot of them, and people treat them as commodities. But they are very dangerous when they go wrong, as evidenced by some recent events at General Motors or Toyota. In both of those cases, the systems did not shut down when they should have. Most cars today, for instance, have electronic throttle control, constantly monitoring. And if it doesn't like something, we shut it down. And I know in my career, having gone through all of that, you really have to take the conservative side and say, I'm just going to shut it down. I may irritate a small fraction of the clientele,
but it's safe.
With false negatives, but that's the safe shutdown. Toyota did not do that with their system. They did not have a redundant system in there, and they did not set it to shut down. And of course, somebody in the GM environment did not understand that turning off the key also disables other parts of the system. But yeah, I think the conservative approach of shutdown, They are highly, highly complex systems.
David, Don, any thoughts? Okay. Your question is so powerful, and let me try to assimilate what I've heard. First, the complexity through the interconnectedness is generating a set of states that no one with any certainty can ever say that there won't be an unintended emergent behavior. And so the introduction of the idea of resilience, okay, was introduced, in which there is, for resilient systems, there are constant monitoring of parts and feedback mechanisms that say, here are allowed controlled environments within parts. Another thing that I heard was architecting as a principle is a way to reduce an effective number of exposed nodes.
Right.
And through the reduction of the effective number of exposed nodes at certain levels of abstraction, it is more easy to put the monitoring systems and then the control laws so that you have an ability to understand if emergent behavior is happening and you can do something. You're empowered, the system is empowered to start to isolate it, shut it down, and handle it from there. And that's a different mindset, I believe, than much of an engineering approach, say, of 30, 40 years ago. There was hidden assumptions, or at least hidden behaviors, where if you watch people, there was a notion of, I can control and bound this totally, right? That if you really cross-examine someone, they would go, of course, I can do it totally. But when you watch the behavior in the mental outset, it was like, I can. And so there's this shift that you're hearing that has to be adopted, whether you're a part engineer or whether you're the engineering of the system, that is going to have to become a almost instinctive element to be able to assure some of this critical system behavior is delivered. Are there other questions?
Just one more comment. You
Yes.
mentioned monitoring it, and we've gotten into situations where the act of monitoring is a problem as
Yeah.
well. So you get into this paradigm that I can't monitor and test the system because the act of doing that fails the system. It's just something else to think about.
Yeah. And I would also look at separating the monitoring, the control, and the protection, because those are three different layers and have to be architected appropriately into the systems.
Yes.
Yeah. Powerful point. There was a hand, yes?
So you talked about managing risk. You talked about the risks that we're likely to see in the future. How do you integrate going new places, using new materials, focusing on new challenges? An example that comes to mind that I think really exemplifies focusing too much on risk and not focusing enough on the task is Robonaut 2 and the DARPA Robotics Challenge, where there were so many redundancies built into the software that it actually shut itself down and didn't complete any tests.
Yeah.
Because it was built not to the DARPA specs for the challenge, but it was built for what it needed to be doing for NASA.
Yeah.
Which was different. So how do you address those challenges, and how do you test the unknown, I guess, when you can't test it before it's active?
Let's start over on this side. Any thoughts triggered by those questions? Okay, I'll give you a break.
I think you brought up the fact that sometimes the monitoring system itself could cause a problem, and building in redundancy can cause problems because it adds complexity, right? In the satellite business, even back in the dark ages, you wanted to minimize the number of parts, but building a redundant system on top of the regular system meant you had more parts. And what if your safe hole system goes berserk, right? So, I mean, you have this problem all the time, and there's probably some point of diminishing returns on building backups and safety valves and everything else. So you have to think about that. I mean, even in the time before there were hardly any computational power on satellites, though, the satellites were so expensive and so hard to launch that they usually all left with some sort of safe hold mode in them as well. So if everything else went wrong, the satellite took over itself and didn't follow all the other instructions they have, and it did basically two things. It pointed an antenna at the Earth so people could talk to it, and it pointed somehow, whether it was a spinner or a three-axis stabilizer, it made sure its solar arrays were pointed at the sun so it didn't run out of power. And maybe that was all it did, until people could talk to it. So you have to look at how complex you want to make your redundancy as well, I think.
Right, but then how do you do something new?
Well, I mean, so interesting enough, the space business is a very conservative business. Sometimes people would say, some people would say, well, you can't fly anything unless it's flown, right? So how do you ever do anything new? And yet the space business has found ways to do this. I mean, one thing they've tended to do is to sometimes have experimental satellites in other ways, or experiments on satellites that are somewhat isolated so they can try some new things out while they're there in new technologies. And if you look at the history of space, my gosh, we've done so many new things in space over the years. So we have found some way to break through that. Again, though, it gets back to the whole thing of, it's not saying eliminate risk, it's saying manage your risk. Understand what you're doing,
Yeah. Yeah, John, did you have something you wanted to add?
Sure. So I haven't heard anybody talk about exploiting opportunity.
And risk and opportunity are the opposite
So,
sides,
so
right?
there's got to be some reason why you're going to take on additional risk. And so you need to come up with what's the proper balance. And it might be that you just want to have a small increment from a solution that already exists, or you want to experiment and you want to fail quickly and you want to learn from those failures and you want to move on. And so that's what I've seen is let's explore some things and let's accept the fact they're risky. Let's make sure no one gets hurt or anything else, but let's accept the fact they're risky and let's learn quickly from those failures and move on.
I would add that for some people, Ray Kurzweil is a visionary. Others think that he might be drinking a little bit too much every once in a while. But his point in your area would be to recognize the computational capacity and the curves that things are going on, and therefore how important modeling is in managing and testing these innovation concepts as they're moving through in a controlled way. We're about halfway through, so I would ask that we hold the questions. First, is everyone okay if instead of taking an extended break, we just take 2 or 3 minutes and stand up and stretch a little bit? Because you have 3 more very, very powerful speakers that I want a chance for you to hear, and then we can pick up the questions again. So how about if we just stand and kind of make a stretch for a few minutes?
Alita?